To open CFDPost, double click on the result section. Yeah, we click on the Z axis so that we will be in the XY plane view. Now, what we will do is we will do volume rendering. To do volume rendering, click on the volume rendering button available below the menu bar. Okay. Now, first in the volume rendering, we will visualize the pressure fields. Domains, all domains, variable is pressure, range is global. If we click apply, yeah, our pressure variation can be seen. It can be seen that the pressure is maximum at the inlet and it reduces to 0. It is obvious. Even for a laminar flow through a pipe, there will be a pressure drop across the pipeline that you can clearly see over here. So now to visualize velocity in the same volume rendering itself, click on velocity. We are more concerned with the u velocity, so we'll click velocity u under the variable, click apply. Yeah, here the thing is, in this front view we cannot see what is happening inside the pipe flow. So to see what is happening inside the pipe flow for velocity, in pressure case is different. Pressure, the pressure does not vary at a particular place along the length. That is, for example, at x equal to 0.2 meters, the pressure will be same at all points at x equal to 0.2. But velocity will be varying along the radial direction. So to see that, we have to cut the pipe and see that. To enable to cut the pipe, there is an option called clip plane. Click on clip plane, click OK. Now XY plane, let our plane be at center, that is at z equal to 0 value. Click apply. Okay. Now in this view, if we want to have a view of the clip plane, right click, clip scene, clip plane 1. Now you can see that see how the velocity is varying. To go into the nearer part, I'll click pan. Here you can see at the initial length of the pipe, it is a developing flow, like boundary layer is getting developed. So the velocity is nearly equal to the initial velocity that we have given, that is 0.05, of the order of 0.05. As we go along, you can see that for a fully developed flow, the velocity is maximum at the center of the pipe and it goes to 0 near the walls. Okay. Now we have done the clip scene. So even with this clip scene, we can just get a qualitative view. To get an exact quantitative analysis, what we are going to do is we are going to plot some graphs. To plot graphs, plotting graphs has 2 steps. First step is creating the location, that along which line or along which points we are going to plot a variable. So first we have to create few locations. We will create, for example, I need to visualize how the velocity profile is varying along the radial direction at a distance of x equal to 0.3, that is at the end of the pipe. To create that, I will create a line. Okay. My line will be of 2 points, that my line is like from here to bottom of the pipe to top of the pipe. So my point 1 will be, everything is at x equal to 0.3. My pipe diameter is 1 centimeter, that is 0.01 meter. So its radius will be 0.005. So point 1 at the bottom will be minus 0.005. Z is at 0. 0.350. Okay. Now we have created one line. So to plot the velocity along the radial direction, now we are going to create a chart. Click on the chart menu, click, you will say fully developed velocity profile. Click OK. Now in the data series, we give the thing as line 1. The x-axis is the radial direction. The radial direction is here is the coordinate y-axis. What we will do is give y, and the value of y changes from 0.005. So we will give some value extra like 0.006 so that our graph doesn't cut off. And y-axis is velocity, not any velocity, u velocity is what we are concerned with. Okay, click apply. Fine. Now you can see that the curve is not very smooth. This has to do with the number of sample points in the location. We will click line 1, double click on line 1 and increase the number of sample points to 1000. Click apply. You can see now the curve has smoothened out. This way we have created the velocity profile. Now to do the same thing, we have to plot how the pressure drop is occurring along the length of the pipe. So again what we will do is we will create a location line 2, let it be line 2. Our point starts from 0, 0, 0 to the end of the pipe 0.3, 0, 0. Let my sample points be 1000. Click apply. See, you can see a line running along the length of the pipe. Now again we click on chart to pressure distribution along length. Okay, we will give a title of the chart, pressure distribution along pipe length. Okay, x-axis will be in this case x itself, y-axis will be pressure, line display, x-axis starts from 0 and ends at length of the pipe. Y data series, our location is line 2, x-axis, y-axis line display. Click apply. You can see how the pressure drop is occurring along the length of the pipe. To verify with the manual calculation, the total pressure drop along the length of the pipe is nearly 6.2 pascals. So I'm just going back to my calculation sheet. Pressure drop across the length of the pipe, it is given by the formula 32 mu LV by d square. This is for a Hagen-Poiseuille flow of a laminar flow through a pipe. So if we use this formula and calculate it, the value that I am getting is 4.8375, but the value that is showing in the graph is 6.4 something. So there is a difference of some 1 pascal. This difference is due to my mesh file. I have done a very coarse mesh for this tutorial. Especially the mesh along the length of the pipe, the mesh is very coarse in my case. So what I would urge you to do is to improve the mesh, like to refine the mesh along the length of the pipe and then run the simulation. That way the pressure distribution will be closely matching with the analytical solution. Now I will show you how to create a report. We have done pressure distribution along length, fully developed velocity profile. To create report, file, report, publish, click OK. You can go to your working directory, user files, and open the report with your browser because it is an HTML file. You can see your report is published.